Hi, Assalamualaikum. Welcome back to my channel Physics 2.5 KSSM. Today, I will discuss on 2.5 Archimedes Principle Part 2. In this video, I will discuss one learning standard that is communicate about applications of Archimedes Principle in daily life. The first application that I want to discuss today is a hydrometer. A hydrometer is a measuring instrument that applies Archimedes Principle to measure density of liquids. So when the hydrometer is stationary in liquid, the weight of liquid displaced is equals to weight of hydrometer. Later we will discuss further about the forces that act on hydrometer. In a less dense liquid, a larger section of hydrometer is immersed in the liquid to displace larger volume of liquid and vice versa. So we will compare between these two liquids. This one sink more, this one sink less. So we can see from here, the volume of the submerged parts is equals to volume of liquid displaced. The hydrometer, if you look at the basic structure, this is a lead shots, glass bulb, okay, and a stem, and the scale that marked here. The largest measurement will be at the bottom part of the scale, and the smallest measurement will be at the upper end of the scale. So later we discuss why the smallest measurement should be here. Okay, the bigger bulb is to increase the buoyant force so that the hydrometer floats. The lead shots is to ensure hydrometer floats upright so that the scale can be read accurately. Okay, so that's the purpose of having this structure. Okay, look at the force that acts on hydrometer and its working principle. The first hydrometer immersed in low density liquid. The second one immersed in high density liquid. Let's assume the two hydrometers are identical, meaning having same mass. For low density liquid, the hydrometer sinks more to depth H1 because it displays larger volume of liquid. For high density liquid, the hydrometer sinks less or floats more to depth H2 because it displays smaller volume of liquid. What are the forces that act on the hydrometer? You can see this is a gravitational force or weight, always act downward, WO. The weight is balanced by buoyant force, always marked upwards, FB. The forces are balanced as the hydrometer float upright, stationary. Okay. So from here, based on the concept of balance forces, weight of hydrometer is equals to buoyant force. Hydrometer floats at stationary state. Identical hydrometers means the hydrometers have same weight. Both hydrometers experience same buoyant force. So why this one sink more and why this one sink less? Due to different in density of liquid. For low density liquid, hydrometer need to displace more volume of liquid in order to produce buoyant force that able support its weight. For the high density liquid, due to the high density liquid, the hydrometer just need to displace small amount of liquid so that buoyant force is equals to its weight. Volume of the liquid displaced always equals to volume of the submerged part, meaning the volume that sink here below the water level. Okay, refer to activity 2.10 in your textbook. So this activity is to use hydrometer to determine density of various liquids. Apparatus required, hydrometer and 300 milliliter measuring cylinders, material, distilled water, olive oil and glycerin. In the lab, you can just choose any 3 types of liquid, different liquid with different density. Okay, based on the value of the density that we can use that measured by the hydrometer. So for distilled water is 1 gram per cm cube. Olive oil is about 0.911 gram per cm cube. Glycerin is about 1.259 grams cm to the power -3. Okay, let's look at discussion. Why does the scale of hydrometer not start from 0? Remember, hydrometer is used to measure relative density of liquid. That is relative to density of water. Density of water is equal to 1 gram cm to the power -3. Therefore, there is no zero relative density of liquid, so there's no zero mark at the scale of hydrometer. Why is a smaller scale reading of hydrometer at the top end of the tube? It always at the upper end. This is because hydrometer will sink more in less dense liquid. That's the reason why we need to mark at the upper end of the hydrometer. State one precaution while carrying out this activity. Eye level must be in line with the lower meniscus of liquid when reading the scale of hydrometer to prevent parallax error. Or you can just write as eye level is perpendicular to the scale of hydrometer, okay, to prevent parallax error. Next is activity 2.11. Aim of this activity is to construct a Cartesian diver to show the working principle of ballast tanks in submarine. Apparatus required 1.5 liter plastic bottle and a test tube that can be inserted into the plastic bottle. Materials, masking tape, water and food coloring. Okay, so to understand this one, let's watch this video. First, observe the level of water in the test tube. Okay, what we do next, squeeze the lower part of the bottle so that the test tube sinks slowly to the base of the bottle. Observe level of water in the tube. Slowly release the pressure on the top so that the test tube moves up again to the surface of water. Observe the change in level of water in test tube. So this is when no pressure is applied to the bottle. So you can look at the level of water in the test tube. Look at what happened when the bottle is squeezed. So you can see water is forced to get into the test tube, and it becomes heavier. The total weight of the tube, does the tube sink. Same thing when you release the pressure, the water will get out from the tube, and then it will float up. Okay, this is Cartesian diver. Actually, this one applies same concept applies to a submarine. Okay. Discussion. How does the volume of air in the test tube change when the test tube moves up from the base of the bottle to the surface of water? Volume of air increase. So you can see when move up, level of water becomes shorter. Means the volume of air inside will increase, thus increase the buoyant force. Explain the movement of test tube by applying Archimedes Principle. When pressure exerted on the wall of the bottle, water is pushed into the tube because you are exerting pressure on the water. So the water will transfer pressure so that the water will get into the test tube. Therefore, total weight of the tube increases greater than the buoyant force. Resultant force downward is produced and causes the tube to sink. Okay. So this is the Cartesian diver, so we can apply the same concept just now. Figure 2.36 shows the ballast tank found in submarine. The working principle of ballast tank in submarine is similar to working principle of Cartesian diver. So you can see when less water in the tube, the test tube will float up or move up and float. When the water gets into the test tube, means more water gets into the test tube, you can see the test tube sink. So same thing applies for the submarine. As you can see, submarine has ballast tank. So when the water is pumped into the ballast tank, the total weight of submarine increases, thus the submarine sink to a certain depth until buoyant force becomes equals to weight of the submarine again. When the water is pumped out from the ballast tank, the total weight of the submarine decreases, causes the buoyant force larger than the weight of the submarine, thus the submarine float or move up and float near to the surface of water. Okay, next this is about ship and plimsoll line. So what is this plimsoll line? Principle line are always marked at the hull of the ship. So you can see the label here, okay, TFF, okay, TS, W, W, and E. So this one we call it standard load line marks. What is this mean? TF means tropical freshwater, F freshwater, T tropical seawater, S summer temperature seawater, W winter temperature seawater, W and E winter North Atlantic. Okay, let's watch this video to understand this concept.
For a ship that carry load, there must be a load limit, as the ship always travel to different density and different temperature of water. So the load limit is marked at the hull of the ship in order to ensure that the part of the ship which sink into the water does not exceed the load limit. The load limit must be installed as a plimsoll line to the ship as a safety features when the ship travel to different density and different temperature water.
Hot air balloons, I will discuss three situations. The first situation, the forces that act on the balloon, you can see from here, weight, total weight of balloon and load, and buoyant force, FB. Inside the balloon, there's a hot air, and this one is the basket that can carry load. Let's say forces are balanced, meaning WB plus WL equals to FB, meaning the total weights of balloon and load is equals to buoyant force. So in this situation, the hot air balloon will float at the same height. Or we can say the balloon is at stationary at certain height. Second situation, let's say when the hot air is heated up, it becomes hotter. So the balloon expands, thus more buoyant force is produced. If buoyant force is larger than total weights of the balloon and load, the forces are unbalanced. Thus the hot air balloon will ascending upwards. So the heating up air in the balloon will increase buoyant force. So in this case, the balloon will accelerate upwards. The third situation, lets the hot air to cool down. So the volume of the balloon will decrease, thus buoyant force decrease. When buoyant force becomes smaller than the total weights of balloon and weight and the load, the forces are unbalanced. What happens to the balloon? The hot air balloon will descending downwards. The cooling down air in the balloon will decrease buoyant force. So this is how we apply Archimedes principle for hot air balloon. So that's all my video today. I will continue 2.5 Archimedes Principle Part 3 in the next video, which I will discuss on problem solving, formative practice 2.5, and some extra exercise. Okay, that's all for now. Thank you for watching. Bye.